Okay, hi everyone. Welcome to this week's Mars seminar. This is our second seminar this semester. Thanks for coming along. So this week we're going to hear from Andrew Baggaley, who's one of our new Mars professors in the department. And Andrew is going to talk to us about vortex avalanches and neutron star interiors. Andrew, over to you.
Thanks very much. Yes, thanks everyone for coming. So I work in two really distinct areas. One in math bio, which is probably more relevant to Mars. One looking at quantum fluids and particularly their applications to neutron stars, which is maybe less relevant. However, I already have these slides prepared, and I didn't have slides on the math bio side easily prepared. So you're getting this. I've stripped out lots of the detail here. So if you've got sort of expertise in fluid dynamics, then some of it may be sort of teaching you to fix the phrase, isn't it? But hopefully this is a talk that everyone finds accessible. And so if you're sat there having no clue what's going on, I'm the one that's failing, not you. So just stop me and ask questions, particularly to PhD students. This is your window to ask stupid questions. Before you get too old and too worried, you can't ask stupid questions because you're going to know what's going on. Okay, so this is some work that I've been doing over the last 4 years now. It's been led by the three of us, so Toby Wood and Carlo Berenghi, who are at Newcastle, and Gary Liu, who's a postdoc who did much of the work on this. So Gary gets all of the credit and prepared the first draft of these slides. So I presume that people have got very little background in quantum mechanics. Is that sort of true? I mean, met the concept of wave. Anyway, you can play with it because it's a nice movie. So the CNRS in France commissioned the production of these movies to explain some particular phenomena, and we're going to watch a couple today because it means you don't have to listen to me, and they're really nice. So the first one is on wave-particle duality. It's the idea of particles behaving both as particles and waves. There is in the name. There is some music, but I don't want to risk too much feedback. Maybe it doesn't play so well, because I guess it's coming through Teams, isn't it? Anyway, it's a bit jumpy. So the idea is this double slit experiment where if you pass particles through it, you've got ballistic motion particles, and you get sort of two bands. When you pass a wave through it, you get this diffraction pattern that forms. And what people found when they started with electrons passing through this double slit, that in this particular experiment, an electron, when you scrutinized it, behaved like a wave. But in other experiments, it behaves like a particle. And so quantum objects have this property of wave-particle duality. And in particular, what's really crucial for what I'm going to stop this thing, I'm going to talk about next, is the idea of how the wavelength of the particle relates to its momentum. So these are the typical patterns that you get without music that you get if you do this experiment with electrons. You can see they mimic this interference fringe that you would get with a wave. And so it's a clue that something complicated is going on. One way it's a really hard thing to think about, and I think that's true of most things in quantum mechanics. These guys in France did this very neat experiment. They've got a lot of press for it. Quite how much it reveals about quantum mechanics isn't entirely clear. But this is an experiment from above where there's silicon oil and they vibrate really fast, but at quite a low amplitude. And then there's a single droplet of silicon oil, and it effectively bounces on the surface and creates a pilot wave below it. And so it's an object that has this particle-like structure that has a wave around it. And I don't have the full movie of them doing the double slit experiment, but you can see this object hopefully interacting with this double slit and then moving off. And what they did in a series of experiments was to show that if you do this double slit with lots of these particles, you build up this interference pattern that you would get that's associated with wave-like behavior. So, as I say, they got lots of press and shiny magazine articles and Nature and whatnot. Quite how much it reveals about what's going on deeper is not entirely clear. So, when this idea of wave-particle duality was put forward and physics was in its sort of golden age of this sort of quantum revolution, I'm sure everyone knows this guy here. This guy, Bose, I won't pronounce his first name, is an Indian physicist who's known for bosons, if you've heard of bosons. We'll talk about bosons quite later. And he realized this remarkable thing that if the wavelength of a particle is related to its momentum, and we know that if I've got this cup of tea here that's quite hot, not as hot as it was, the particles here have quite a lot of momentum, that's what's giving it heat. If I take this and cool it, the momentum of the particles lowers. And what he realized was, and then if these were quantum particles and had an associated wave with them, the wavelength would increase as I reduced the momentum. And he put forward this idea that there was some critical temperature where the wavelength of the particles would correspond to the same distance, effectively the distance between the particles. And these waves would start to overlap, and you might have some sort of coherent quantum object over much larger scales than an individual electron, say, or an individual atom. And he wrote to Einstein and they published this work, and however many years later, not half a century, but a long time later, these three physicists realized this fifth state of matter. So you've got your three classical states of matter that we learned in school: plasma, typically astrophysical objects, and this was this fifth state of matter that was discovered. These chaps got the Nobel Prize for it. If you go and see one of these experiments, all you see is lasers. So these are light experiments, effectively, but you can look through a little microscope effectively in them and visualize these gases effectively. And this is the famous image that they found where above a certain critical temperature, this thing behaves like a classical gas. Let's not worry about why this looks like a classical gas. The particles effectively have a certain distribution. Their momentum follows one distribution. And there's this prediction below critical temperature, there's phase transition and the underlying momentum distribution switches, and you get this switch to Bose-Einstein statistics. And so that was very neat. And again, one of these nice little animations that hopefully tries to put what I've said in words into a very nice video format. So it is a bit jumpy as compared to what I'm seeing on the screen, but these particles move round, and in a second, I just not talk over it, but it's hard to stop that urge. You sort of see that they start to associate some wavelength with these particles. And we're dropping the temperature, and you get to some critical temperature where each temperature is associated with a momentum and then a wavelength, and eventually there's this coherent matter wave, this sort of superatom that you realize it's called a Bose-Einstein condensate. And the reason why that's interesting, for me at least, is the fluid dynamics of this object are really, really interesting. So this is with very cold gases. There's another almost field in its own right where which is associated with Bose-Einstein condensate, and that's the helium systems. And Lancaster for many years was famous for having the coldest temperature in the universe. That's assuming that there's no kind of intelligent matter out there. And there's this Lancaster cryostats where they chill superfluid, still chill helium down to incredibly low temperatures, where it also becomes a superfluid and has many of the properties that I'm going to talk about. And so as this project evolves, the guys over in physics are running experiments that are going to look similar to the theoretical setup that I will hopefully show you, and then we can start to try and compare what the theory predicts and what their experiments are showing. So I'm presuming really no background in fluid dynamics. I think that's probably safe to do so. So this is a classical fluid. So this is a fluid like the tea in this cup or the water in bottles, in that it's not constrained by quantum dynamics. And this is a snapshot of a storm. I can't remember what the storm was called, coming in from across the Atlantic. And what we're visualizing here is effectively a vector. Right, we've got visualization. This is the wind speed. We've got pressure coloured, and we can see that the west coast is common. We're getting hammered with wind and presumably rain. We can measure certain properties of a fluid motion. So U here is just a two-dimensional vector field. Here, in reality, it would be a 3D vector field for the atmosphere that represents the velocity field. And we can do these contour integrals around and associate a quantity called the circulation. And the only thing that's constraining the motion of this fluid is essentially how much energy I put in and the system size. I clearly can't have something, a hurricane or a storm system or whatever, that exceeds the radius of the Earth or whatever it is. And the strength of it is constrained by sort of how much energy I can put in. That's obviously one of the issues with climate change, that we are raising the amount of energy in the system for things like storms. So if you're familiar at all with quantum mechanics, you know that when quantum mechanics comes into play, it typically constrains lots of things, constrains energy levels that, say, electrons can take, and gives us chemistry. And when it comes in fluids, it constrains the fluid motion. And so this is an experimental snapshot of one of those laser tables that I showed you. And what I've shown here, these won't really make sense until I show you a few movies slightly later on. This is the density field of the gas, and these black spots are holes. So if you let out the plug on your bath or your sink after you brush your teeth or in a bath or whatever, you get this whirlpool vortex that forms. And you can think of each one of these as being like a very miniature version of one of those vortices that form. But the circulation that they can take is constrained by atmosphere. And typically, they effectively have a charge, but a circulation of either plus or minus 1. And if you've met any fluid dynamics at all at undergraduate level, the thing that you do is this thing called the point vortex model, which is a very idealized model for a classical fluid like this storm here. People still use it, but actually it's a very, very good model for quantum fluids because these vortices are point-like. Like I said, if this doesn't make sense to you now, well, you can tell me, but I'll play some movies that are probably going to be a bit jumpy slightly down the line that hopefully we'll go back to this slide and kind of try to understand what all of this is here. So the title contains something about neutron stars. You might be thinking, not talking about stars here. So before we get to stars, we know that nearly probably every astrophysical object rotates to some degree because of conservation of angular momentum. So if we're starting to think about stars, it starts to make sense to think about what happens if we rotate a superfluid. So you won't see it, I won't be able to do it, but imagine if I rotate my cup of tea, or I have a bucket of water and I have a record player or something that spins it round. In the end, I'm going to reach some equilibrium, and I can describe it mathematically. It's called solid body rotation. And you know this phenomena when you go on a roundabout at the park, that the outside is moving faster than the inside, and it's a linear velocity. The problem that a superfluid has, if you think about it, we go back to this picture here, if all of these vortices have a fixed size and a fixed strength, how do you mimic that solid body rotation? Because I can't just have one big vortex at the centre. I have to have these little individual guys. And so what you see is something collectively takes place. So when you rotate a superfluid, people have visualized this in the helium experiments and the gas experiments that I talked about. When you rotate this system, you see the system being threaded by this vortex lattice. These holes create this uniform lattice, and mathematically you can analyze the structure of this to understand what the minimum energy configuration is. Unsurprisingly, it's hexagonal because nature likes hexagons, and you can estimate how many vortices you should have to limit the right solid body rotation. And what you find is as I'm rotating faster and faster, the faster I rotate, the more vortices have to appear. Okay, so that's what happens if I take one of these guys and spin them. Okay, so that's the sort of background on superfluids. I am going to come back and try and explain that experimental picture a little bit better shortly. But now, neutron stars, which seem about as unrelated to what I've talked about with people doing these laboratory experiments as could be, as you could have. So this is a really famous image in my age. Maybe less of a famous image to you guys. This is one of the first images that came out of the Hubble telescope, which was an image of the Crab Nebula. So this was first observed by Chinese astronomers a long time ago, and they observed a bright flash in the sky. And what we think they observed is this event is a supernova, so a very large star exploding, and this creates this very complex fluid motion, which is effectively what you're visualizing here. And what's left, the sort of core of the star that's left, collapses in on itself and can become one of many different objects depending on the mass that it has left. So the most extreme example you can have is a black hole. Likes black holes, but they're fairly boring objects. One that's much more common is something like a white dwarf. So the universe is threaded with white dwarfs. But if your mass is just right, or falls between those two limits of being able to be a white dwarf, you're too heavy for that, you're not heavy enough to become a black hole, then the path that you take is to form a neutron star. So a lot of this is physics that I think we can skip over, kind of what dictates the collapse. If you're interested, or if you know a bit about sort of electron degeneracy pressure and then neutron degeneracy pressure, basically comes down to that. This is a more modern photo that's been taken from, I think, the James Webb telescope, where it's the same patch of sky, visualized slightly differently. And right at the center of this is this tiny object. So this star, when it exploded, was orders of magnitude larger than our own sun. And what's left at the end after this very extreme explosion and then this runaway collapse is an object that's about the size of a city, about 10 kilometers. Lancaster is, it's probably Lancaster size, and it has about 1 to 2 solar mass left at the end. So the star originally was much heavier than that. What's left is sort of cranking something the mass of the sun down into something the size of Lancaster. So these are extremely extreme objects. They effectively contain all of modern physics in a single object. You've got people in gravity groups, so there's a big gravity group in the Maths department at Southampton who are interested in these objects for gravitational waves, relativity. They contain nonlinear elasticity in the crust. And the reason why I'm interested in them is they're the only object we know of that is a natural superfluid that's not created in the lab. There are also people who suggest that dark matter may well be a superfluid, but that's sort of more speculation in a theory. With neutron stars, we're incredibly confident that they are superfluids, and we've got evidence for that as well. These are hard objects to visualize. The sky is big, and 10 kilometers a long way away is not very big, but we've got observations that also fit with the picture of having a superfluid in these objects. Okay, this is just a pretty picture if people are starting to get a bit bored by me. This is a simulation someone's done of the actual supernova process, put the equations of fluid dynamics effectively into a computer and run a numerical simulation where you inject a huge amount of energy. There's magnetic fields, which complicates things, but all the kind of mathematics of this is quite well developed. What you find, and what you might be thinking if you still are paying attention to me, is stars are quite hot. And this star that was quite hot was just undergone a massive explosion. I was talking about Lancaster recording the coldest temperature on Earth, and all of the superfluid experiments that we have are cold. We have some that are at room temperature, but that's still cold compared to this. After the explosion, these stars collapse, and they do cool down in time, but they are still pretty warm. I've got the sort of temperature up here, so we're measuring temperatures and things in kilo electron volts. Probably isn't a huge amount, but they're pretty warm. 1,000, probably warmer than 10,000 Kelvin, something like that. You can see some of the things. So 1 to 2 solar masses, extreme densities. Who knows what density 10 to the 15? But who knows what it means? You can't really think about it. What's important is not the absolute temperature of this system. What's important is the relative temperature. So the densities here are so extreme that we're really at the density of not an atom that's got huge amounts of empty space, but at nuclear densities. And so what you find after the stars cool down is that they're incredibly cold. Much colder than you would need them to be to undergo this transition to forming a superfluid. So these guys, at the end of a very extreme life, are left with very cold, very dense objects. But there's still a lot going on. Because of this collapse down to an incredibly small object, all of the angular momentum, lots of got blasted off, but much of the angular momentum is conserved. And so these things spin incredibly rapidly. If you talk about things like millisecond pulsars, the person who observed these first was Jocelyn Bell. She was there, now she's Jocelyn Bell Burnell, and she missed out on the Nobel Prize for the discovery. Her 2 elderly male colleagues took the prize instead. Astronomers have these classifications of what they name stars, and neutron stars, and you might have heard of pulsars. They effectively mean the same thing. They don't have this classification now, but the first one that she sort of suggested, tongue in cheek, was LGM 001, LGM 002, where this LGM was little green men, because it was sort of the idea of something was flashing so rapidly, this flashing I've not explained, but I will do in a second, that it must come from some intelligent life trying to send some signal to us. So what we actually see are a kind of subset of neutron stars that we call pulsars. So again, this little movie, it's not rendering particularly well. What I see is this moving quite smoothly and rapidly. From the poles of these objects, we typically have these bursts of very high intensity electromagnetic radiation. And if we're lying in the right plane relative to the star, as it rotates, we see this bit of this object. And that's how we can detect these things that we've got called pulsars, because they look like they were pulsing. So I don't need to focus too much on this if I get a bit too much into the physics, but they have a stellar structure that we can kind of estimate. Nuclear physicists estimate, but crucially for what I'm interested in, doing some fluid dynamics down the line, is that there's a region within the star that we think is super. Some solid crust, which is the thing that we basically observed. There's a big bit in the middle where people have no real idea of what's going on, but there's this region where we think that the neutrons are being compressed so strongly that they can condense, they become this state of matter called a superfluid. And so it means that if these stars are rotating very fast, which we know they are, we expect lots of these vortices that I showed you on the previous slide. So what do we observe? Well, if we've got this thing flashing, I don't know why I'm going back when it didn't play very well, but anyway, we've got this thing flashing. We can measure these bits, and so we can measure the period, so the time difference between one bit and another. And this is what is observed. And the thing to say about these things as well is that they contain very, very strong magnetic fields. So there's a mathematical theorem that you can prove about the conservation of magnetic flux. So if you've got this large magnetic field and then you collapse into a very small object, you bring all of that, what of that magnetic field with you. And if an object that's magnetic is rotating, then it experiences a breaking force. So these things with very, very strong magnetic fields are experiencing this breaking. And so these are old pictures, I'm afraid, and aren't great. But what's plotted here is the period of the star's rotation. And you see it increasing in time, which makes sense. So the gap between the bits is getting larger because this rotating thing is being slowed down by having this large magnetic field. So you see it in one star. My mouse is also a bit slow, sorry. You see it in this one star on the left where it's increasing. We'll get to the jumps in a second. And you see it in this other star here. And it's a constant line. And then all of a sudden, there's this break. And it looks like the star has spun. So the period of rotation has suddenly dropped. And this is what happens if you look at kind of effectively derivatives of this signal. You see that the slowdown rate is constant. And then all of a sudden, this is very zoomed into an actual event. You see this jump. And people started to call these things glitches because effectively you've got this system that you can understand. It's like a big bar magnet that's rotating really rapidly. So it experiences this braking force and slows down. And then all of a sudden, it's like this magical energy comes out of nowhere and kicks this heavy object really, really hard and gets it to rapidly spin. Like if you've got almost like a plate spinning on a stick, it's slowing down, and every now and again you get a smack and it spins back up. That's what you're seeing in this here. And that was quite puzzling to people. And then people started to really analyze lots of stars and looking at the statistics of these events, and found that they were characterized by all the things that you see in self-organized critical systems. It's a whole field of mathematics, theoretical physics, interesting systems which are called self-critical. And the most common example of these is a sand pile. So this is a sort of canonical example where you've got this pile of sand here, you've got a constant injection of sand from above, and what you see created are avalanches where the waiting time between one avalanche and the next follows an exponential distribution, and the size of these avalanches has a parallel distribution. And depending on the slope, you might have the mean of the process is not defined. And so you can have some very large avalanches that can be created. And that's what people started to see in neutron stars. And so what people got interested in was trying to understand where this big kick could come from. And the idea is you've got this superfluid that sort of sat inside, and it doesn't know that the system's slowing down. But it's got some sort of coupling to this solid, real crust, a classical crust that's not a superfluid, it's a classical object. But every now and again, there's some coupling where the superfluid can spin down very, very rapidly and transfer that angular momentum to the thing that we see, causing it to spin back up. So a simple model on that will almost be like a capacitor. When the difference between the superfluid and normal crust drops, gets too large, sorry, that suddenly there's a kick, there's an injection of rotational energy from the superfluid into the crust. And this is getting too much into the physics of it, but the way that we can understand this coupling is in this region called the inner crust here. As you're moving down through the star, the density is increasing. And this crust is a kind of ionic lattice made up of nucleons that you wouldn't get on Earth. Maybe you can kind of create in very extreme experiments where you've got a certain number of protons in these kind of nucleons, and you're packing more and more neutrons into it. And then you get to a certain density, gravity is large enough, that these neutrons can no longer be packed in anymore. And they start to leak out and raise these drips. So you get this phenomenon called neutron drip, where you end up with a lattice, and between this lattice is this liquid, this fluid of neutrons that we think is a superfluid. And so the object that's effectively coupling the crust to this superfluid is this lattice. And so you've got these vortices embedded in the lattice, and everything's rotating, and one of them is slowing down, the other one is not. And that's the system that we're interested in. So here's a sketch. So we have one of these vortices. I've only shown them actually in 2D really, and explain them carefully. In 2D, these things are like little spots. In 3D, they're space cubes. They're one-dimensional space cubes. So you can imagine around this blue line, there's flow moves around. So think of these as being like very thin bathtub. That's the best way to picture it. I am going to play some movies that I hope will kind of give you a little bit of a feel for how they work. So I think this really is what I've said. You've got this kind of lattice of these vortices that are rotating. You've got this crust structure embedded in it that's spinning down. There's some complicated coupling that we're going to try and model mathematically, capture mathematically, and then we're going to see if we can reproduce this glitch-like behavior and some of these interrogate the distributions of many of these glitches that we can produce through numerical simulations and see if they capture some of the physics of the real system. So that's what I've said. That's the picture, that this sort of capacitor-like picture. So how are we actually going to model this? So I don't know if many of you will have met the Schrödinger equation before. A few of you. So you might, if you've done some quantum mechanics as part of undergraduate course, have met the Schrödinger equation, which basically looks like this without this. This would apply to a single quantum particle. And typically what you do is look at kind of a single quantum particle trapped in like a box potential. So this V is the potential, where you think of this as how the system is confined. This is effectively going to be a model for the crust of the system. You get to it. But we've not just got one single particle here, like we have in a one particle system that would be subject to just a Schrödinger equation. We've got many particles. And so we've got a term that accounts for particle-particle interaction. So we make lots of assumptions that I won't go into, but what it boils down into some complicated integral where if we can make the assumption that it's very, very unlikely that three particles are going to interact at the same time, there's a delta function, everything collapses, we can write an equation down. And that's true for the experiments that they do on Earth in gases, where the kind of laser one that I showed you. That's a really good assumption. For the human experiments that they do, which was physics that way, well, for physics it's a really bad assumption. For neutron stars, nice. I mean, neutrons aren't even bosons. Two kinds of words here. Neutrons aren't even bosons, which really is subject to Bose-Einstein condensates. They're fermions, so there's some additional process That's the process that's behind superconductivity to get these things to form what are called composite bosons. That's just, anyway. We can write down an equation that sort of models some of the system, a feel for the system. And to get a sort of insight into this equation, we can just write down this is a complex scalar field, psi, and we can do what's called the manual transformation, that really is just a modulus and argument, plugging it in, turning the handle, equating real and imaginary parts. And what we find is an equation, if you've done any fluid dynamics, should be very familiar. So this is the equation of fluid dynamics. You meet in graduate course on fluid dynamics. This effectively is like a Euler equation with a weird term at the end that you would never see in a classical fluid. So this equation, I think the key point here before I kind of lose everyone, is that this is an equation that has something to do with fluid dynamics trapped inside it, even if it doesn't seem to do it first. So do we need to worry about this? All right, probably a little bit. So we can associate the density, so how many atoms there are in a particular region, with modulus squared of this field, and we can associate the velocity. If you think back to that storm that I showed you coming in, then the velocity field of this gas, or neutrons in the star, if you think we can stretch the model, is the gradient of the fields. And the rest of it we don't need to worry about. So we can do some analytics with the nonlinear Schrodinger equation. It's commonly called the Gross-Matthievsky equation. You're not going to remember that. We can call it the GPE. That's the equation we're studying. We can say what happens if we've got like a quadratic bucket that we put our atoms in, and find out what profile it should have. And what we find is that the density has some spatial variation. There are more atoms in the center of this track than there are at the edge, which is probably what we'd expect. And we find that the phase, this is not particularly interesting, and this would just sit there forever, not doing a huge amount. We can also put vortices into the system. So this is this hole, and this vortex is associated with a phase. This is now the argument of that complex scale field. And if we took the gradient of this, what would it do? It would give us circular trajectories that we wouldn't. This is like a vortex that we would get in a classical fluid. The one would swirl leaves outside. If we're sat here, we would rotate around this object. And we can put more than one vortex in. Again, this is a movie, so it's not going to play very well, but these are two vortices that have opposite signs. So one has one rotation direction, the other has the other rotation direction, and they will move as a dipole pair, they move as a single object, and then they interact with the back. Don't need to talk too much about that now, but you can see this phase field evolves in time along with the density. And the last example, just to give you a feel for this, is if we put in two vortices that have the same sign. So you're going to two vortices that would rotate in the same direction, and they do what you might imagine they would do. They rotate around. And so I realize I might actually end up being time pressured, but if I jump back to this very early slide, and we go back to that experiment.
You need to start showing.
Okay. We go back to this experiment. That's what you're visualizing. Those dots, the dots are the same holes as we had in my movie. So in time, this can move in some complex, chaotic way. And this is very, very hard to do with experiments, as you might imagine. But this is an attempt to reconstruct that phase. And so you can see around this object, that gradient for phase there is this rotation. Okay, so I'm blabbering on now. So let's cut to the sort of punchline, because I do want to kind of talk about where there can be an interaction with sort of the data science statistical part of Mars, which maybe doesn't seem very obvious right now, but we'll get to it. So we're going to do some numerics. Let's skip through this really quickly. There's a numerical method that's trivial to do. If you can do a Fourier transform, and if you've got access to Python or MATLAB or whatever, you could do a Fourier transform in a line, then in about 15 lines of code, you can solve this system numerically. This rotating, it's a bit harder because of the angular momentum operators not diagonal in Fourier space, so you can basically solve it, and it's easy. And we will skip over all this because I'm going on. We aren't the first to look at doing this model. Lots of people have done this. There's lots of paper where people have tried lots of different mathematical models, Rostovsky equation, point vortex, which is comes from classical fluids, and tried to mimic these glitches in neutron stars to see whether this picture of a superfluid embedded in some complex kind of landscape can give you back self-organized criticality, essentially. And at first sight, it looks pretty good. So this was a really early setup that people did back in 2010-11, where you've got a small number of vortices where in that lattice configuration I showed you earlier, because the system is rotating, and the colour scheme isn't great, it's black and white, because people worried about journal printing costs back then, but these grey dots are pinning sites. These are meant to mimic those the elements of the nuclear lattice. And why these are important, you can almost think of these as like lazy boy chairs, bucket seats. A vortex would really like to see, ideally. There's an energetic cost to it coming out of the lazy boy chair and getting a beer. But there's also a cost to not aligning with the right frame of rotation. So essentially two competing forces on the vortices in this complex, in this system. One where they want to sit and do nothing, because they're quite comfy. Another one where they really want to leave the system. And it's the kind of competition of these two that's interesting. Fluid dynamics tends to be, interesting fluid dynamics tends to be kind of competitions of timescales, competition of forces that are quite closely balanced. So you get lots of interesting mathematics and physics out of systems where there are these sorts of competitions going on. And what they saw is basically they cranked up these grids. So you can think of this number V naught as being the depth of my lazy boy chair. Okay, if I make this really large, I start to see this jittery line in the spin down of the star. So this is their model of the spin down. And this looks pretty good, right? So if there's no pinning, this thing spinally smooths down, as you might expect. And if they bring up this grid, then suddenly it gets jittery, and you could sort of say, well, these look a bit like glitches that you showed me a few pictures ago, so we've done it. The problem is this contains, can't count them quick enough, but what, 20 vortices, 20 dots there, something like that. The real system has 10 to the 15 dots, some unimaginable number of these vortices. And so you're doing quite a lot of extrapolation work there. And the main issue is that each one of these glitches is just one vortex leaving the system. And this idea of kind of self-organized criticality typically requires some collective behavior. So I've got my sand pile, and it's a few grains of sand becoming unstable at the bottom that suddenly allow all the rest of the grains to form this avalanche. It's some sort of collective phenomena. One vortex popping out clearly isn't what you call collective. They did the right thing. They suddenly went, well, we can't do 10 to the 15, but we can go from 20 to 200. And sort of try to sort of work asymptotically. And what we find is kind of what worried us when we started this project. All of that effect basically gets washed out. Everything, all these little jumps just get averaged out. What they did that was a bit disingenuous is they kind of took a derivative of this and zoomed in to the level where it started to look jumpy again and said, oh, look, we do have something. But really what you're wanting to see is tens of these vortices interacting collectively, and then try to interrogate that by building a more simple model, say, that captures that dynamics. That wasn't what they saw. So let's go a bit quicker. We do a big simulation, and it doesn't look massively bigger than the one that they did. There's a lot that's going on behind the scenes here. This is quite a long simulation because we spin the system down very, very slowly to mimic the slow spin down at the start. Lots of details that don't really need to care about. The question is, when we do this, can we see something that looks like the real system? And we think we can. So this is kind of the main takeaway slide. I'll spend a little bit of time on it. So this is the rotation rate of the super. So technically it's the angle rate of the super. And so what we see is there are regions where it just plateaus. It essentially doesn't know that the star, if we can think of this as a star, it's a bit of a stretch, is spinning down. And then there are these regions where you get this huge drop in the angular rate. And that's exactly kind of what we want. So these events, these drops, and those ones, are associated with this rapid spin up of the crust. We're not modeling the crust here properly. So everything's in the superfluid. You can almost think of the opposite image of this as being what the crust would do. It spins down slowly, then when you get this large drop, suddenly it spins back. And if we look, these events are all coupled. And if we look over here, you can see these trajectories of the vortices. So this is how the vortices are moving, coloured by time. And what we see is when one of these events take place, we do have something that looks correct. We have 10, 15, if you stretch it, maybe vortices that interact together and give something that does resemble collective motion. And there's lots more I could say about that. Let's watch a movie. Let's jump in. There may not be a huge amount of point watching it because it kind of, if it plays smoothly, it's okay, but if it's just jumping, yeah, I'll leave the movie. If anyone's interested, you can come and have a look on the laptop. I think it's also online as well, so this has been published earlier this year. And so there's lots of things that we're interested in doing. So this idea of collective motion, if we look at, if we kind of zoom in on these trajectories, we see there can be periods where the vortices sort of like stream, and there are periods where the vortices are rotating around one another. And we can try to build models for that, inspired by what people have done in the field of collective motion. So this is a huge field where people are interested in the formation of human stampedes, death spirals in ants, and stampeding behavior. And so that's a kind of avenue that we're investigating. And maybe this is even more clear. We can see something where if I told you that these were fish swimming in a tank, you might believe me. Well, so yeah, that's all very interesting and very nice, and we can interrogate the statistics of these glitches and try to convince ourselves that you log something, always get a straight line power law, so you definitely get a power law, and we can sort of say, does this look like it follows an exponential distribution? It's sort of, it's not definitive, but it looks in agreement. And we can build sort of simple toy models. That's typically a way that we can get a lot of insight into fluid dynamics. We can do these large simulations and couple them with analytic models where we can do something like linear stability analysis to try to understand what's going on. So where can this fit in with Mars? What are opportunities? there is something with neutron stars, maybe I'll get to that. So we had in one of these EPSRC small maths grants to do parameter inference, and we never actually did it. We did reinforcement learning that I can talk to you about. This again isn't the movie, it will be a bit jittery. These again, these dots, these vortices, and they're moving around and interacting. And what you'll see if you care or stare at this for long enough is the number of dots is decreasing in time. It's analogous to if I stir a tank of water or line the bath and I splash around, the bath water will stop swirling eventually and will go back to being a yes station before. And that's what's going on when this system relaxes back to equilibrium. And I can try to build simple models for something like the number of vortices. What's the number of these dots? I can try to construct simple models based on simple arguments about vortices leaving the boundaries, vortices interacting. And these models have some free parameters. And so our approach was going to be to do some simple MCMC on this system. In the end, we went down a rabbit hole of reinforcement learning, doing something that, not doing this, but doing something else with reinforcement learning. Like probably there's a can of worms to describe. The other opportunity, so people are really interested in these things, not just as models of stars, but as matter circuits. So this is almost like the matter equivalent of superconductivity. Superconductivity are electrons flowing without resistance. Here are atoms in the gas. I never really mentioned these are typically things like sodium, rubidium, period-long elements. We can make little circuits, and these circuits are very, very simple at the moment. People can realize these in the lab. They can create a flow along the circuit in the same way as you can put a battery and turn it on and create a flow of electrons. What you can do with these that you can't do in a circuit is if you want to create a superconducting circuit or electric circuit in general, you kind of get your wires, solder them together, put your battery on, whatever, your power source, and away you go, and that's it. Your circuit is fixed. If you want to modify it in time, you've effectively got to turn the experiment, turn the system off, do some rewiring, turn it back on. Because of the way that these are trapped, we can dynamically change the configuration of the circuit in time. So think of like the wires in your electric circuit being able to move around in space. You can create these three-dimensional flows of matter waves. At the moment, they're very simple. As you can see here, they're kind of rings, so we've got flow along the rings. But these are remarkably accurate sensors of rotation, of accelerations. Whether you're going to have these in devices soon, it's not clear, but you can create room temperature equivalents of superfluids. They're more complicated. Could you use something like reinforcement learning to optimize the design of this particular circuit and improve accuracy of the sensor? Why did I say optimization? So this will be the final thing, I think. So this is the opposite problem of the neutron star, because I couldn't put the movie together very quickly. These are, again, these thin sites, these lazy boy seats. And what I'm going to do now is spin the system. And there are certain neutron stars where that's actually a reasonable model, where they're accreting matter from a nearby partner star. And what you'll see is vortices start to be created, and then they move into the system, and they want to go and sit on these holes. These dots will move in, and they'll find somewhere to live. And eventually, everything calms back down. If I do the same again, but now I perturb that lattice, and we have good reasons to think this lattice could have some irregularity to it, have some sort of more complicated design than the kind of periodic lattice that I showed you, then the trajectory of these vortices is going to be different. The overall end configuration of the system is going to be different. And if I spin this guy back down, try to recreate what I did, it could well be that the distribution of glitches looks different. And so what could be done with optimization or reinforcement learning is to try to understand what is the optimal design of this lattice that captures either data from experiments or the lab data that they're producing over physics, which I didn't talk about, but they're effectively embedding an aerogel in their cryostat, which mimics these prongs, these seats for the vortices to sit in, and are then spinning the system down. Okay, so I'll finish there. Gary, the postdoc who wrote the slides, kept fantasizing about Ferrero Rochers when he looked at the design. He's from SARS. Yeah, thanks very much for listening. Sorry if I lost you.
Thank you, Andrew. I think unfortunately in the interest of time, we have to finish here, but of course, please feel free to stick around if you have time.
I've got to take it down.
But you know, Andrew is local, so
Yeah, come and have a chat.
yes. Thanks for coming along. So we were supposed to talk in 2 weeks' time, but from an external speaker, but they unfortunately cancelled. So we will either have someone stepping in local in 2 weeks' time. If not, we'll have a seminar in 3 weeks' time. I'll keep you all updated. Thank you.
Sorry, I've lied.
Yes, you had said that.
Yeah, that's I blame them.